Now the 11th inequality we have is Schur's inequality. Now Schur's inequality says if we have three non-negative real numbers x, y, z, so these are non-negative real numbers, and we have a positive real number, say t, then xt into x minus y into x minus z plus y to the power t into y minus x into y minus z plus z to the power t into z minus x into z minus y. It is always greater than or equal to 0. Now this inequality is known as Schur's inequality. Now for this inequality, if we take t as 1, then we can write this summation x, x minus y, x minus z, and this is symmetric sum. It is greater than or equal to 0, or we can write this as x cube minus x square y plus x square z plus xyz greater than or equal to 0. So from here we can write this x cube plus y cube plus z cube plus 3xyz is greater than or equal to x square y plus x square z y square x plus y square z plus z square x plus z square y. Now we can rearrange this right hand side as x cube plus y cube plus z cube plus 3xyz, and if we take these two together we can write xy into x plus y, taking these two yz into y plus z plus xz into x plus z, and if we take t as 2, then it will be this symmetric sum of x square, and this is x minus y, x plus z greater than or equal to 0, or x square, and this is x square minus y plus zx plus yz greater than or equal to 0. And if we simplify this, we can write x to the power 4 plus y to the power 4 plus z to the power 4 plus xyz into x plus y plus z will be greater than or equal to x cube y plus x cube z y cube z plus y cube x plus z cube y plus z cube x. So these are two standard results from Schur's inequality which we are going to use while solving inequalities. Now let us take an example. Say for example, it says if a, b, c are non-negative real numbers such that a plus b plus c is 1, then prove that a cube plus b cube plus c cube plus 6abc, it is greater than or equal to 1 by 4. Now what we can do is we can write this as 4, and this is a cube plus b cube plus c cube plus 6abc, it is greater than or equal to 1, and we can write this one as a plus b plus c whole cube. Now this is 4 a cube plus b cube plus c cube plus 6abc, and will be greater than or equal to a cube plus b cube plus c cube plus 3 a square b plus c plus b square c plus a plus c square a plus b. Now we can cancel a cube plus b cube plus c cube, and we can cancel 3 also. Then we get a cube plus b cube plus c cube plus 8abc will be greater than or equal to a square b plus c plus b square c plus a plus c square a plus b. Now we know that since ABC are non-negative real numbers, then a cube plus b cube plus c cube plus 8abc will always be greater than or equal to a cube plus b cube plus c cube plus 3abc, which is greater than or equal to a square b plus c plus b square c plus a plus c square a plus b, which is standard result from Schur's theorem. So that means this inequality is true. Now let us take another example, and here we given a plus b are 3 positive real numbers such that a plus b is greater than or equal to c, b plus c is greater than or equal to a, and c plus a is greater than or equal to b. Then we have to prove this result. What we'll do is we'll say let a equals x plus y, b equals y plus z, and c equals z plus x. Then if we take a plus b is x plus 2y plus z, it is greater than z plus x. So from here we can write x, y and z are non-negative real numbers. Now if we substitute the value of ABC here, then we can write this is 2, and then x plus y square, and b plus c is x plus y plus 2z. This symmetric sum and will be greater than or equal to x3, and symmetric sum of x plus y whole cube plus 9 times x plus y, y plus z into z plus x. Now we can write this as 2 times summation x plus y cube plus 4 times this summation z into x plus y square. It is greater than or equal to summation x plus y cube plus 9 times x plus y, y plus z into z plus x. And if we are going to simplify this, we'll get x cube plus y cube plus z cube plus 3xyz, that is greater than or equal to x square y plus z plus y square z plus x plus z square x plus y, which is nothing but result from Schur's inequality when r is equal to 1. Now this 13th inequality that we want to study is Holder's inequality. Now Holder's inequality says if we have sequences AI, BI up to ZI, each containing n elements, then this inequality A1 plus A2 plus AN to the power lambda A into B1 plus B2 plus Bn to the power lambda B up to Z1 plus Z2 up to Zn to the power lambda Z will always be greater than or equal to A1 to the power lambda A, B1 to the power lambda B up to Z1 to the power lambda Z, plus in the same way we'll write it for A2, B2, Z2. So A2 to the power lambda A, b2 to the power lambda b up to z2 to the power lambda z will continue up to an to the power lambda a, bn to the power lambda b up to zn to the power lambda z. This inequality holds if lambda a plus lambda b plus lambda z it is equal to 1. So sum of all these powers it must be equal to 1. Only then this Holder's inequality it is going to hold. Now one thing that we should keep in mind for Holder's inequality, we cannot get maximum or minimum value of expression from Holder's inequality, because this inequality it gives us an upper bound or a lower bound. So if from Holder's inequality we get a result that x is greater than or equal to some a, then this a may not be the least value of x. Now how do we use this inequality? For this we'll take up an example. Suppose it says we have two real numbers a and b such that a to the power 6 plus b to the power 6 equals 64. Then we have to establish an upper bound for 3a square b plus 4a b square using Holder's inequality. So in this problem we have to establish an upper bound for this expression when we are given that a to the power 6 plus b to the power 6 is equal to 64. Now for this question we will consider three sequences. First one is 3 square 4 square. Second sequence is a to the power 6 comma b to the power 6, and this third sequence is b to the power 6 into a to the power 6. Now we have to choose their power such that sum of lambda a plus lambda b up to lambda z it is equal to 1. So we'll choose power of this as 1 by 2, this power as 1 by 3, and this power as 1 by 6. Now if we add all these three, we'll get this sum as 1. So now we can use Holder's inequality for these sequences. So we can write 3 square plus 4 square to the power 1 by 2 into a to the power 6 plus b to the power 6 to the power 1 by 3 into b to the power 6 plus a to the power 6 whole to the power 1 by 6, and it is greater than or equal to, now a1 to the power lambda, so it will be this 3, b1 to the power lambda b, so a to the power 6 to the power 1 by 3 is a square into, and this is c1 to the power lambda c, b to the power 6 to the power 1 by 6 is simply b, plus, and then this is a2, so it will be this 4, and then b square and a. Now this is under root 25, which is simply 5, and here it will be a to the power 6 plus b to the power 6 whole to the power 1 by 2 will be greater than or equal to 3a square b plus 4a b square. Now a to the power 6 plus b to the power 6, it is 64. So this value will be 8. So we can write 40 is always greater than or equal to 3a square b plus 4a b square. So the upper bound of this expression, it is 40. Now it is an upper bound, and it necessarily doesn't guarantee that the maximum value of this expression is 40. This thing you have to keep in mind whenever you are using Holder's inequality. Now let us take another example, and here it says if a, b, c are positive real numbers, then prove that a upon under root a square plus 8bc plus b upon under root b square plus 8ca plus c upon under root c square plus 8ab it is greater than or equal to 1. Now one way of using Holder's inequality is if we have three sequences, suppose abc, pqr and xyz, then we can write aq plus bq plus c cube to the power 1 by 3 p cube plus q cube plus r cube to the power 1 by 3 into x cube plus y cube plus z cube to the power 1 by 3 will be greater than or equal to apx plus bqy plus crz, or simply we can write a cube plus b cube plus c cube into p cube plus q cube plus r cube into x cube plus y cube plus z cube will be greater than or equal to apx plus bqy plus crz whole cube. So this is an important form which is mostly used in Holder's inequality. Now here what we'll do is we'll take this as a cube, b cube, c cube, and the same expression as p cube, q cube and r cube. So we can write this cyclic or symmetric sum a upon under root of a square plus 8bc into this symmetric sum a upon under root of a square plus 8bc into this symmetric sum of a into a square plus 8bc and will be greater than or equal to, now this is a cube, p cube and x cube. So if you multiply them, we'll get a cube, p cube, x cube. Now a square plus 8bc will cancel. We'll get this as a cube. So value of apx will be simply a. So it will be greater than or equal to a plus b plus c whole cube. So now we can write this symmetric sum a upon under root of a square plus 8bc whole square into, now this symmetric sum will be this a cube plus b cube plus c cube and will be 8abc plus 8abc plus 8abc and that will be 24abc and will be greater than or equal to a plus b plus c whole cube. So we have written this using Holder's inequality. Now we have this one standard result, and which is a plus b plus c whole cube. It is always greater than or equal to a cube plus b cube plus c cube plus 24abc. Now using this result here, we can write this symmetric sum of a upon under root of a square plus 8bc whole square into a cube plus b cube plus c cube plus 24abc will be greater than or equal to this expression. It is greater than a cube plus b cube plus c cube plus 24abc. Now this 24abc part will cancel. So from here we can write this symmetric sum of a upon under root of a square plus 8bc. It is greater than or equal to 1, or we can write a upon under root of a square plus 8bc plus b upon under root of b square plus 8ca plus c upon under root of c square plus 8ab. It is greater than or equal to 1, which is what we need to prove in this question. Now the 14th inequality that we're going to study is Weierstrass inequality. Now there are two forms in this inequality that we use, and this first form is if a1, a2 up to an, they are positive real numbers, then for n greater than 2, we can write 1 plus a1 into 1 plus a2 up to 1 plus an will be greater than 1 plus a1 plus a2 up to an, which is very simple result. And its second form is, if we have n numbers a1, a2, an such that they lie between 0 and 1, then for n greater than or equal to 2, we can write 1 minus a1 into 1 minus a2 up to 1 minus an will be greater than 1 minus a1 minus a2 up to minus an. Now let us take up an example, and it says we have to prove that 1 minus a1 into 1 minus a2 up to 1 minus an, it is less than 1 upon 1 plus Sn, where Sn is sum of all these numbers a1 plus a2 up to an, where each of ai, it lies between 0 and 1. Now to prove this, what we'll do is, we know that any ai will lie between 0 and 1, then ai square will also lie between 0 and 1, and 1 minus ai square will be less than or equal to 1. So from here we can write 1 minus ai will be less than or equal to 1 upon 1 plus ai. Now if we take this product over all I, then this product 1 minus ai will always be less than this product 1 plus ai. So now we can write 1 minus a1 into 1 minus a2 up to 1 minus an will be less than or equal to 1 upon 1 plus a1 plus 1 plus a2 up to 1 plus an. Now we also know that 1 plus a1 into 1 plus a2 up to 1 plus an will be greater than 1 plus a1 plus a2 up to an, which is 1 plus Sn, and if we take the reciprocal, then 1 upon 1 plus a1, 1 plus a2, 1 plus an will be less than 1 upon 1 plus Sn. So it will be less than 1 upon 1 plus Sn. So from here we can write 1 minus a1 into 1 minus a2 into 1 minus an will always be less than 1 upon 1 plus Sn, which is what we need to prove in this question. Now let us take another example, and it says if n is a positive integer, then prove that 1 into 3 into 7 up to 2 to the power n minus 1 upon 2 into 4 into 8 up to 2 to the power n will be less than 2 to the power n upon 2 to the power of n plus 1 minus 1. Now we can write this as 1 by 2 into 3 by 4 into 7 by 8 up to 2 to the power n minus 1 upon 2 to the power n, or we can write this as 1 minus 1 by 2 into 1 minus 1 by 4 into 1 minus 1 by 8 into 1 minus 1 upon 2 to the power n, and we know that 1 minus a1 into 1 minus a2 up to 1 minus an, it is always less than 1 upon 1 plus Sn, and Sn is 1 by 2 plus 1 by 2 square up to 1 upon 2 to the power n. Now this is nothing but a GP. So if we write this sum 1 plus 1 by 2 plus 1 by 2 square up to 1 upon 2 to the power n. We know that it will equal to a into 1 minus r to the power n, and here number of terms is n plus 1 upon 1 minus r. So it will be this 2 and then 2 to the power of n plus 1 minus 1 upon 2 to the power of n plus 1. Now this 2 and 2 will cancel. So this value, it will be 1 upon 2 to the power of n plus 1 minus 1 upon 2 to the power n. So from here we can say this 1 into 3 into 7 up to 2 to the power of n minus 1 upon 2 into 4 into 8 up to 2 to the power n will always be less than 2 to the power n upon 2 to the power of n plus 1 minus 1. And finally, our 15th inequality is Muirhead's inequality. Now this inequality simply says if we have two sequences AI and BI, which are sequences of real numbers such that AI BI belongs to R, and each sequence containing n terms such that this sequence AI, it majorizes this sequence BI. Now what does that mean? It simply means that A1, it must be greater than or equal to B1, A1 plus A2 must be greater than or equal to B1 plus B2, or in general this summation AI, where I varies from 1 to j, it must be greater than or equal to this summation I varies from 1 to j bj for all j lying between 1 and n, and this sum I varies from 1 to n ai must be equal to this sum I equals 1 to n bi. Here it should be this bi. That means a1 plus a2 up to an, it must be equal to b1 plus b2 up to bn. So if we have these conditions, then we'll say sequence AI majorizes the sequence BI. Then this Muirhead's inequality says for all non-negative xi's, then for all non-negative xi, we can write this symmetric sum of x1 to the power a1, x2 to the power a2 up to xn to the power an will always be greater than or equal to symmetric sum of x1 to the power b1, x2 to the power b2 up to xn to the power bn. If sequence AI majorizes sequence BI, then symmetric sum of x1 to the power a1, x2 to the power a2, xn to the power an is always greater than or equal to x1 to the power b1, x2 to the power b2 up to xn to the power bn. Now we take up an example. Suppose we have two sequences 5-1 and 4-2. Now clearly 5, it is greater than 4, and 5 plus 1 equals 4 plus 2. That means this sequence 5-1, it majorizes sequence 4-2. So now we can write this symmetric sum a to the power 5, b to the power 1 is always greater than or equal to this symmetric sum a to the power 4 b square, where a and b are non-negative real numbers. So from here we can write a to the power 5 into b plus a into b to the power 5 will be greater than equal to a to the power 4 b square plus a square b to the power 4. Now let us take up an example.
अब हम आते हैं हमारे 11वें मेथड पे और इसमें हम यूज करेंगे म्यूरहेड इनइक्वालिटी, MUIRHEAD, म्यूरहेड्स इनइक्वालिटी, कि हमको प्रूव करना है a अपॉन b प्लस सी प्लस b अपॉन सी प्लस ए प्लस सी अपॉन ए प्लस बी ये बड़ा है या बराबर है 3/2 के। अब ये जो लेफ्ट हैंड साइड है इसको हम लिख सकते हैं समेशन a अपॉन b प्लस सी, इसका साइक्लिक सम, इसको हम लिखेंगे समेशन a स्क्वायर अपॉन ए बी प्लस ए सी। अब हमने T2's लेम्मा पढ़ा है और T2's लेम्मा ये कहता है कि समेशन एक्स आई स्क्वायर अपॉन ए आई ये बड़ा होगा या बराबर होगा समेशन एक्स आई होल स्क्वायर अपॉन समेशन ए आई के, जहां पे एक्स आई सेट ऑफ रियल नंबर्स है और ए आई सेट ऑफ पॉजिटिव नंबर्स है। तो यहां पे इसको हम लिख सकते हैं कि ये बड़ा है या बराबर है a प्लस बी प्लस सी होल स्क्वायर अपॉन, और यहां पे हो जाएगा 2 टाइम्स ए बी प्लस बी सी प्लस सी ए। तो इसको अगर एक्सपेंड करते हैं न्यूमरेटर को तो ये हो जाएगा आपका ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर प्लस 2 ए बी प्लस बी सी प्लस सी ए अपॉन 2 ए बी प्लस बी सी प्लस सी ए। यहां पे ये सेकेंड पार्ट को कैंसिल कर लेते हैं तो इसको लिख सकते हैं 1 प्लस ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर अपॉन 2 ए बी प्लस बी सी प्लस सी ए के। अब अगर इसको देखें ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर और ए बी प्लस बी सी प्लस सी ए, तो ये जो लेफ्ट हैंड साइड है ये मूरहेड का सीक्वेंस है 200 और ये जो दूसरा सीरीज है ये है मूरहेड का सीक्वेंस 110। तो क्लियरली ये 210 110 को मेजराइज करता है। तो यानी इसका मतलब ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर हमेशा बड़ा होगा या बराबर होगा ए बी प्लस बी सी प्लस सी ए के। तो यहां से ये जो वैल्यू आएगा वो आपका 1/2 या 1/2 से बड़ा आएगा। तो यहां से हम लिख सकते हैं दिस इज ऑलवेज ग्रेटर देन इक्वल टू 1 प्लस 1/2। तो ये हो जाएगा आपका 3/2 जो कि है हमारा प्रूफ। तो ये क्वेश्चन को हमने सॉल्व किया है T2's लेम्मा से, जो कि एक कॉन्सिक्वेंस है कॉचीज इनइक्वालिटी का और मूरहेड्स इनइक्वालिटी से। अब हम आते हैं हमारे 12वें मेथड की तरफ और इस मेथड में भी हम मूरहेड्स इनइक्वालिटी का यूज करेंगे। अब इसके लिए हम क्या करेंगे, ये जो हमें दिया है a अपॉन बी प्लस सी प्लस बी अपॉन ए प्लस सी प्लस सी अपॉन ए प्लस बी, ये बड़ा है या बराबर है 3/2 के। तो हम इसको सिंप्लीफाई करेंगे तो ये हो जाएगा a इंटू ए प्लस सी ए प्लस बी प्लस बी इंटू बी प्लस सी ए प्लस सी प्लस सी इंटू बी प्लस सी ए प्लस सी, और ये बड़ा है या बराबर है 3/2 इंटू बी प्लस सी ए प्लस सी एन ए प्लस बी के। अब ये सिंप्लीफिकेशन हम पहले ही कर चुके हैं तो हम वापस से इसको सिंप्लीफाई नहीं करेंगे, तो हम डायरेक्ट इसका रिजल्ट लिखेंगे। तो सिंप्लीफिकेशन के बाद ये आता है आपका 2 टाइम्स ए क्यूब प्लस बी क्यूब प्लस सी क्यूब is greater than equal to a square b plus ba square b square c plus c square b plus a square c plus c square a। तो अब ये लेफ्ट हैंड साइड को देखें तो ये मोरहेड का 300 है, और ये जो राइट हैंड साइड है ये मोरहेड का 210 है, और ये पहला सीक्वेंस दूसरे सीक्वेंस को मेजराइज करता है। तो मोरहेड्स इनइक्वालिटी से ये रिजल्ट ट्रू है, तो इसका मतलब ये कंडीशन भी आपका ट्रू होगा। तो ये है हमारा 12वां प्रूफ।